This is Professor Ricardo Jimenez. Today we're going to see the gated oscillator that starts without delay. All the typical oscillators are present the issue that they must have a delay before starting to oscillate at its expected frequency. In this oscillator, you can see here the timing diagram. Let me adjust the illumination a little bit. And in this timing diagram, you can see that this is the control signal. This is the output frequency of the logic, the output logic right here from the oscillator. And you have here the voltage, the capacitor's voltage VC, which is the voltage right here at this point, from here to ground. So when the control signal is low, initially, of course, the capacitor will reach the maximum VDD because you have a 0, so you have logic 1, and the current will charge the capacitor to its until it is fully charged. So that's why I start at this point, and the output is high. So when the control signal goes high, the capacitor, because the control signal is high and the capacitor was charged, fully charged, now the output goes to logic low, which is T0. And the capacitor starts discharging, even though you see here a straight line, it is not a straight line, it is a logarithmic, graph. So the capacitor starts discharging, crosses VT plus, and then reaches the negative threshold voltage, VT minus. And once it reaches the VT negative, the input, the NAND gate input, consider this as 0. And because this is logic 1, and now it goes back to logic 1. So, the output goes back to logic 1, T1, and starts charging the capacitor again. When it reaches VT plus, so now both have 1 on 1, the output becomes 0, which is T2, and it starts discharging. So the T1 and T2 is the standard period for the frequency. Of course, the reciprocal of T is the frequency. But the problem here with this oscillator is T0, because it took this time to start charging. So this presents a problem when you are using these oscillators in instrumentation applications as a base frequency oscillator. It happens that this will affect your readings always. And of course, you can adjust it with other techniques, but it'll affect your readings. They will not be accurate. Now, to solve this classical problem, I have here a solution. So, but first, we have to see that T0 is the time for the capacitor to discharge. So when the capacitor is discharging, it presents a voltage drop across resistor R, because this is to ground. So the current goes to ground. And that current is equal to VDD over R. And so the current, the resistor's voltage is equal to the power supply voltage times E to the negative T0 over RC. Right here it has to be negative. So from this equation, because this equation is obtained by the current, so the current flowing across this circuit is the current is equal to VDD given by the gate over R times e to the negative T over RC. From that equation, we get the voltage resistor. And that voltage resistor, let me adjust the illumination. Yeah, that voltage resistor is this. Solving for T0, we get T0 equal to RC ln of VDD over VR. because the resistor will reach this voltage when the capacitor is discharging from VTT to VT negative. So from VDD to VT negative is the voltage the resistor will reach. So we substitute VR by the VT negative, and this is the T0 formula or equation. So this is the delay. That's the good thing of this. You know the delay you will have before it starts oscillating. Okay. Now to solve that issue, we apply, we get this circuit. Put it right there. We get this circuit where you can see that now we still have the control signal, and right here at the output, as I said in the article, it's better to use the unused NAND gates right here as buffers to isolate the frequency from the RC network. That way you won't change, you will not consume any current. And in this circuit, you can see here that now to solve the issue is to keep the capacitor, instead of having the capacitor fully charged to discharge and get the T0. Now we will hold, we will place a 0 here, the output will be 1, so a current will be always trying to fully charge the capacitor, but we will eliminate that by placing a diode. This is a diode, and the diode goes to a trim pot. This should be a trim pot. This is not a diode, this is a trim pot, 500K or any other value, as long as it is greater than 10K, 20K. And right here, you adjust the threshold voltage. So this point and this point, when the capacitor starts, is willing to fully charge, you hold that voltage at a level a little bit less than the negative threshold voltage. So if the negative threshold voltage is 2.8, you will hold it here at 2.7. So that will be by adjusting the voltage here to a voltage less than 2.7, as long as this diode is conducting. Now so the capacitor will stay there. But when you apply the control signal high, now when you have a 1 here and a 1 here, now the output will be 0. So the capacitor will start discharging from VT positive to VT negative. So you have to hold here the voltage to VT a little bit less than VT positive. I said before VT negative, no, it's VT positive, okay? And once VT positive is 2.8. So in practical terms, we can say 3 volts most of the time for the 74HC132, 3 volts. So you adjust the voltage here in such a way that the diode will be conducting, and you will have a voltage a few millivolts less than the VT positive. So when this is 1, the capacitor from VT positive will be discharging immediately to VT negative, okay, instead of discharging from VDD. Okay, so this can be seen here in the graph. So when this is 1, the capacitor which reaches VT positive a little bit less, a few millivolts less than VT positive, avoiding to trigger in the gate, of course. And then you can see how the discharge starts here. And now you didn't have to start from here, from VDD, from high volts. So you start from VT positive to VT negative, VT positive and VT negative. And now you can get the frequency immediately and accurate, and that way you will be able to use it in your instrumentation designs. So notice here that T1 is RC, because there's only one resistor, RCLN, or VDD minus VT negative over VDD minus VT positive. and T2 RC ln of Vt positive over Vt negative. So the equation T1 considers the Vt negative because it is discharging it is discharging from Vt positive to Vt negative, but Vt positive is the initial charging voltage, and this is the voltage, the final discharging threshold point. Okay, and the frequency output is the sum of T1 plus T2. So by applying logarithmic terms, we convert the sum into a product. That's why ln RC ln A plus RC ln B, it's RC ln of A times B. So we do the product of this term by the product of this term. And this is a classical equation everybody uses in an oscillator, but now we don't have the delay T0. Once we get these values, in this case 2.8, 1.8, 5 minus 1.8, 5 minus 2.8, you get a constant here, you get an ln, which is a constant k, and that constant k you can put it on the numerator by applying the reciprocal loss and algebra loss. So another issue that I have always noticed in these designs is that you have always to consider the tolerance of your elements. Sometimes students tell me, Professor, I'm not getting the frequency I was expecting. And when I see their designs, they're using 5% or 10% resistors, most of the time 5%. And the capacitor tolerance is the most critical part, because sometimes you're using 20% tolerance or even higher. So that will change your frequency 20% of this formula. So that's something you have to consider. And of course, this resistor in the feedback, if you use a resistor that a metallic resistor with a very low ppm, parts per million, it'll make your design more stable, okay, like a metallic resistor. Okay, and so that's what I was willing to explain about this design. And of course you can submit your comments. And I want to say that as a final thing here, that there are once you are putting here the diode, there are diodes that have a voltage 0.7, 0.6, but you can get a germanium diode with a voltage less than 0.3, 0.2 volts, okay, and that'll be even better to adjust it right here. So this is a brief summary of my article. And in another article I will talk about the equations, how we are getting equations for the RC networks, because right here we're applying them, but we will see the analysis of all these three types of equations. Okay, thank you, bye.